Effect of synthesis techniques on the structural properties of cobalt-doped zinc nanoferrites. Abstract cobalt-doped zinc, CoxZn1-x Fe2O4, nanoferrites for x equals 0, 0.1, 0.4 has been synthesized both by microwave hydrothermal and chemical co-precipitation techniques to witness the effect of two different synthesis techniques on the structural properties of cobalt-doped zinc nanoferrites. All the samples with hydrothermal method were calcined at 7000 C for 4 hours with the application of 2.54 GHz microwaves for 10 minutes, whereas samples with chemical co-precipitation method were annealed at 700 degrees Celsius for 6 hours. The geometry of the crystals was studied by X-Ray Diffraction analysis, XRD, and the structural properties including particle size and lattice parameter were calculated from XRD data. The average crystal light size was calculated using Debye-Scherer formula, which lies in the range of 5.41 nanometers to 3.25 nanometers by hydrothermal technique and 6.23 nanometers to 5.58 nanometers by co-precipitation method. Lattice parameter of the samples sintered by both hydrothermal and co-precipitate methods are first increases from x equals 0 to x equals 0.1, and then a decreasing trend is observed with increased concentration of the cobalt due to the transfer of Co2+ ions from octahedral to tetrahedral sites. The morphological study has been carried out using scanning electron microscopy, SEM, to investigate the effect of co-dopant on the structural properties of Zn Fe2O4 nanoparticles using both the techniques. Keywords: microwave hydrothermal, chemical co-precipitate method, structural study, cobalt-zinc ferrites. Introduction. Nanotechnology is introduced for the reduced size and single-phase particle, helping to design the efficient devices at higher frequency and low cost. The nanoferrite synthesis sturdily depends upon preparation technique because incongruous technique strongly affects the crystal structure, physical and chemical properties, and even the applications one. For a long time, researchers have been searching for a material synthesis method with easy procedures, outstanding performance, and low cost 2 to 3. The synthesis methods of inorganic powder materials includes many methods in which the solid phase method results in a high yield and is easy to realize for large-scale industrial production. However, because of the limitations of the equipment and the process itself, it is difficult to control the particle size, purity, and morphology of powder using the solid phase method 5. The liquid phase method mainly includes the precipitation 6, hydrothermal 7, and sol-gel methods 8. The advantages of the liquid phase method are convenient operation, simple synthesis process, and controllable particle size. Cobalt-zinc ferrites have attracted the attention of the researchers because of their first-class chemical stability, mechanical consistency, high electromagnetic properties. These properties of ferrites made them to be used in the electronic devices 9, 10. In this paper, a comparative study is carried out to monitor the effect of two different synthesis techniques on the structural properties of cobalt-doped zinc nanoferrites. For this purpose, microwave hydrothermal and chemical co-precipitation techniques are considered due to their high purity, small and homogeneous nanoparticle size, energy saving, minimal heat exposure of the reactants, low temperature and low cost synthesis techniques, range and short time sample preparation. 2. Experimental techniques. Ferrite nanoparticles CoxZn1-x Fe2O4, x equals 0, 0.1, 0.4, were prepared by chemical co-precipitation and hydrothermal process respectively. In order to attain the desired compositions, stoichiometric amount of Fe, No3, 3. 9H2O, Zn, No3, 2.6H2O and Co, No3, 26H2O were dissolved in distilled water with constant stirring. Neutralization was carried out with NaOH solution by adding it drop-wise to obtain light brown precipitates. 2.45 GHz microwaves were employed for 10 minutes in case of hydrothermal method, and mixture was cooled and transformed into the flask for autoclave at 1210 C for 1 hour. Whereas, the reaction temperature was kept at 90 oC in co-precipitate method until the precipitates settled down. Using both techniques, the pH was maintained and samples were centrifuged at 3600 rpm for 5 minutes, were dried at 2000 C for dehydration. The dried powder was mixed consistently with an uncontaminated agate mortar and pestle, and annealing was done at 700 OC for 6 hours. The samples were allowed to cool slowly at room temperature for fine grinding. 3. Results and discussions. X-ray diffraction technique is used for the structural analysis of all the acquired samples using CUK radiations with wavelength equals 1.5418 A. The 2. Range was adjusted between 20 O to 100 O with the step size of 0.050. The X-ray diffraction pattern of the prepared samples are shown in the Fig 1a, and Fig 1b, for x equals 0, 0.1, 0.4, for hydrothermal and co-precipitate methods respectively. The figures showed a sharp peak pattern with no extra reflection peaks in the diffraction pattern, which confirms structure of the synthesized material. The persistence of major lattice planes in the given XRD pattern confirms the configuration of the crystals with spinel cubic structure having space group FD3M. The peaks were indexed with JCPDS cards, hashtag 22-1086, and hashtag 89-1012, and card number 9,006,894. The prominent peak of the sample shifts towards the higher theta values due to the difference in the radii of the cobalt, 0.78 AO, and zinc, 0.82 AO, ions 11. A. Hydrothermal method. B. Co-precipitate method. Fig 1. X-ray diffraction pattern of CoxZn1-x Fe2O4 at x equals 0, 0.1, 0.4. A. Variation of particle size with composition. In XRD, spectrum width of the highest peak, 311, is used to calculate average particle size by using Scheurer's formula 10. D equals 0.9/scos. I. The particle size of the samples with increase in concentration of co-doping from x equals 0 to 0.4 in CoxZn1-x Fe2O4 obtained both by hydrothermal and co-precipitate methods. The particle size varies between 3.25 nanometers to 5.41 nanometers acquired by hydrothermal technique, whereas particle size for the same composition of co-doping using co-precipitate method lies in the range of 6.23 nanometers to 5.58 nanometers as shown in Fig 2 and mentioned in Table 1. In both the cases, crystalline size first increases at x equals 0.1 because the distribution of dopant changes with increasing concentration of co till it reached to equilibrium, and then for further increase in co-concentrations it decreases, as the distribution of dopant becomes regular at higher values and cobalt ions, 0.78 A, replaced with zinc ions, 0.82 A. Moreover, the reduced and precise particle size by hydrothermal method is obtained by changing the controlling parameters, such as applying the microwaves for 10 minutes instead of reported in literature 7, 11, and for co-precipitate method is due to sintering temperature and time of sintering 6. The dependence of the lattice parameter A on the cobalt concentration is shown in Fig. 3 for hydrothermal and co-precipitate methods respectively, which shows a mixed behavior with the increase in cobalt content in the prepared nanoferrites due to disorder in crystal because of the large ionic radius of Co2+, 0.78 AO, compared to that of Fe3+, 0.645 A0, and ionic radius of Zn2+, 0.82 AO, than that of Co2+, 0.78 AO, 12. C. Variation of despacing with the composition. The variation of the cobalt content with the interplanar distance, despacing, is mentioned in Table 1. It is clear from the data that first despacing increases from x equals 0 to x equals 1 and then decreases by further increase in co-concentration both by hydrothermal and co-precipitate methods, which is attributed with the lattice strain produced by the cobalt ions. From the XRD results, it is being proved that the prepared nanoferrites of cobalt-doped zinc ferrites have mixed spinel structure, which means that octahedral sites would be accommodated by Co2+ and Fe3+, and the tetrahedral sites by Zn2+. When Zn ions get substituted at tetrahedral site with that of Fe3+, the Fe3+ moves on the octahedral site and get attacked with co-ions 11, 12. The replacement of the cobalt ions with zinc ions reduces the ionic radii, which causes a decrease in the d spacing. Scanning electron microscopy, SEM, studies surface morphology of the synthesized nanoparticles obtained by both the methods has been identified by using scanning electron microscope, SEM. It is evident from SEM micrographs, as shown in Fig 4, that the grains present in the samples by hydrothermal method are more evenly distributed with few voids and pores due to release of large number of gaseous products 13, whereas the nanoparticles prepared by co-precipitate method are agglomerated and less uniform. Fig.5 SEM micrograph for x equals 0.0, 0.1, 0.4. 4. Conclusions. Cobalt doped zinc nanoferrites, CoxZn1-x Fe2O4, were synthesized by using both microwave hydrothermal and chemical co-precipitation methods to observe the influence of two different synthesis techniques on the structural properties of cobalt-doped zinc nanoferrites using the precursors such as nitrates of cobalt, zinc, and iron with 99.9% purity. The formation of spinel structure was confirmed by X-ray diffraction analysis with 2 ranging from 200 to 1000. The average crystal light size was calculated by Debye-Scherer formula indicate that the size of the particles are sensitive to the method of preparation, which lies in the range of 5.41 nanometers to 3.25 nanometers and 6.23 nanometers to 5.58 nanometers by hydrothermal and co-precipitation methods respectively. The lattice parameter and d spacing of the samples sintered by both the techniques shows mixed behavior due to the replacement of ions and lattice strain produced by the cobalt ions. The SEM images show that co-doped zinc nanoparticles are in agreement with XRD results.